In this presentation, we will be talking about reliability and survival and how to conduct these tests in SAS Jump. The purpose of reliability and survival tests include evaluating and improving reliability of a product or a system, and determining the quality and how safe the product or system are, and analyzing survival data, or how long something will last before failure, for people and products. There are many different procedures for analyzing data with reliability and survival in JUMP. Some examples are a life distribution, fit life by X, recurrence analysis, degradation, reliability forecast, reliability growth, reliability block diagram, survival, fit parametric survival, and fit proportional hazards. The procedures for getting intended results in SAS Jump include clicking the Analyze drop-down menu, selecting reliability and survival, and then selecting one of the procedures for analysis that were previously listed. In this presentation, we will demonstrate and analyze a life distribution and fit life by X. For the life distribution, you select a time as the Y variable and select a sensor to put in the sensor spot. You can also select a failure cause, frequency, label, sensor code, and confidence interval method depending on the data available. For fit life by X, we select a Y as the time, we select an X variable and a sensor. We can also add the frequency, by, sensor code, relationship, nested model test, distribution, and confidence interval method. The fit life by X is a life distribution where a specific X variable is selected to determine if that factor has any effect on the lifetime to failure.
In order to use the life distribution, we will select Analyze, Reliability and Survival, Life Distribution, then Time in the Y and Sensor in Sensor. After clicking OK, you can see that we may use whatever distribution fits the model best or fits the parameter the best.
Using the fan sample data, these are the results for our life distribution example. The event plot on the left shows when inspections were taken, and it was noted if the product had failed or not. If a product did fail, we know that it failed sometime within the interval between the last inspection and the current inspection time. This is censored data, which is necessary for reliability and survival. We can then compare different distributions to see which ones are the best fit for our data. Here we have selected log normal and non-parametric. As you can see in the distribution profile, we are using the log normal distribution to estimate how many would have failed at a certain time. The ENGI represents the errors in the model, and the smaller the value, the better, as well as the Bayesian and the likelihood to determine parameters. These values are not compared between different models, but within one model itself.
In order to use the fit life by X, we will select Analyze, Reliability and Survival, fit life by X, and choose Time for Y and Sensor for X.
For our fit life by X example, we use the default sample data. We use our hours as time and the temperature is Celsius. There is a scatter plot that shows temperature versus time and shows that as temperature increases, failure occurs sooner. These are the results of our two examples. For this fan sample data, with our life distribution example, we can see that the intervals vary for different samples. As time increases, there are more failures, and the median time before an engine fan fails is about 25,418.67 hours. For the default sample data, our fit life by X example, we can see that as temperature increases, the device fails sooner. The probability of failure is much lower at lower temperatures over time, and much higher for higher temperatures as time goes on. We can see that 40 degrees Celsius is the optimal temperature. The results for reliability and survivability are very important and applicable to real-world situations. Not only can we use reliability and survival methods to evaluate and improve reliability of products and systems, but this can also be used to analyze survival data for people. It's very popular for medical treatments, cancer survival data, and other sicknesses. It's also very important for survival of products that have a great impact on the safety of society, such as bridges, airplane engines, and industrial building foundations.